All right, today's question is number complement, and it's all about bit operators. Like our solution is going to have, some right shifts, bitwise not, bitwise and, a left shift, ones everywhere. But if you haven't seen any of this before, don't worry, we're gonna take it slow. Okay, so in this question, what they want us to do is say your input is 5. We have to realize first that 5 has a binary representation, and it looks something like this, 1, 0, 1. And then what they want us to do is they want us to output the number where we invert each bit. So 1 becomes 0, 0 becomes 1, 1 becomes 0. And this has the value of 2. So this is what we want to return. Okay, so we look up Google and we go like, okay, what are some bitwise operations that we can use in Java? And you might come to a page like this, and they talk about this unary bitwise complement operator. So this is the bitwise not, and what it does is it inverts it. 0 becomes 1 and 1 becomes 0. So perfect, this seems like something that we can use. How come our solution can't just be something like where we just return the bitwise not of this number? Okay, so let's try that then and see what happens. So we try it, and we find out that we end up with this number, -6, instead of our expected 2. And the reason for that is because we're storing our number inside an integer, which has 32 bits. The storage has 32 bits. That means even though 5 is represented with these 3 bits, inside of an integer, there's 32 bits of them. Or, sorry, let me just write it out. So here's our 5, but in an integer, what it actually looks like is there's a bunch of zeros ahead of it, zeros that we're not using. I'm not going to use all, I'm not going to draw all the zeros, but you can imagine that they're there. And then what's happening here is that when we invert it, so when we do not 5, so our bitwise not on 5, we're going to invert every single one of these as well to get this number. And this number happens to be -6. But this is not the same number as 2, which has, the regular all zeros ahead of it. Okay, so that's keep track of the tools that we have. So first we discovered about this bitwise not operator, and what it does is if you not something like 110, then this becomes the number 001. Okay, so we learned one operator, but we see that it's not quite enough to get where we want. They share the last 3 bits as our desired answer, but we have all of this junk ahead that we really don't want. So what we want to do here is we want to introduce the AND operator. Specifically, we want to AND it with a number that we're going to craft ourselves. And this number is going to be called our mask. Okay, so first, a little thing about AND. It's another bitwise operator, and you do something like X and Y. So for an example, let's say X is 1, 1, 0, 0, and Y is something like 1, 0, 1, 0. What happens when we AND it? Whenever you see a 0, the answer is automatically a 0. So there's a 0, there's a 0, and here, since these are both 1s, we get 1. Okay, so how does that help us? Well, we're going to AND it with our mask. And then what we'll craft our mask to look like is we're going to have zeros everywhere except for the last 3 bits, which we care about. So that means when we do this operation here, we're going to get, 0, 1, this becomes 0, 1, 1 becomes a 1, 0, 1 becomes a 0, and then these, because we've set these to 0, we know that these are all zeros. So this is the 2, the answer that we want. So what a mask does is that it, you retain all the values that you set 1 as, so these values remain the same, and then everything that you set a 0 will automatically get cleared out to zeros. Okay, so now the question becomes, how do we create this mask? So I'll put this not 5 up here. And now we're in the process of trying to create this mask. So our mask, we require it to have 0, 0, 0, and then, ones in the places that we care about. So how do we create this number? Well, we note that this number is actually the result of a very simple subtraction. So if we have a number like, okay, just for convenience, I'm going to get rid of all these leading zeros, but just know that they're still there. If we can create a number like 1, 0, 0, 0, if we minus 1 from it, we're going to get 0, 1, 1, 1. So you can think of this in our base 10 world. If we have 10 and we minus 1, we're going to get 9. So 10 minus 1, we get the largest value of this digit beforehand. So that means 1, when we minus 1, this becomes a 0. So 10 minus 1 becomes 0, 9, technically. And then all of this digit gets set to the biggest. So I guess that's not a better example. I think that illustrates it better is, let's say we have 100. Minus 1 gives us 99, or 0, 9, 9. So that's what we're doing here, but in base 2 land. Okay, so now we have a new question, which is how do we get this 1, 0, 0, 0? So now we're going to bring in the idea of a left shift. So what a left shift does is, let's say you have some sort of a number, like say 0, 0, 1, 0, and then you tell it I want to left shift it one time. Then what happens is you're going to get a number like 0, 1, 0, 0. So a left shift basically, like what the name says, it shifts everything to the right by a certain amount. So in this case, by 1. So our goal to create this number is, what number can we create? For sure, we can create 1. And what we want to do is we want to left shift it by the number of important bits here. So there's 3 important bits. So we want to left shift it by 3. So the result of this operation will give us 1, 0, 0, 0. So that, later we can do minus 1 to get 0, 1, 1, 1 from, if we recall from earlier. Okay, so now we have another problem. How do we know that these 3 bits are the important ones? So how do we know that these are the 3 important bits? Okay, so they come from the very beginning, from our original number 5. So remember, 5 is represented as 0, 1, 0, 1. So you can see here that these 3 bits are the most important. So it's kind of like saying, let's say in base 10, we have a number like 46, that the important digits in this number, even though we have all these leading zeros, are these last 2 ones right here. So same thing in 5, and then in our binary version, the important ones are these last 3 bits. Okay, so how do we get that it's these 3 bits in particular? We're going to use something called the right shift. So what this right shift does is it just does the same thing as a left shift. So let's say you have something like 0, 0, 1, 0. And then if you right shift it by 1, you'll get a new number called 0, 0, 0, 1. So it shifts it to the right. And then whatever was there before, it just gets shifted off and it's gone. Okay, so how can this right shift help us? Well, let's see what happens if we right shift it by 1. So we'll right shift this number by 1. We get the following number. So here is the end of our number. We right shifted by 1. So now we have 0, 1, 0, 0. So this 1 technically got shifted off, but then since it's now no longer part of the number, we don't care about it. So it looks like that. Okay, so let's right shift this again. We get 1, and then the 0 becomes here, but we don't care about it. And then let's right shift it one more time, then we get just 0. Everything is 0 now. So here in total, we've shifted it 3 times, which is exactly the number of important bits that we wanted to figure out. So the idea here is we have our 5, and then what we want to do is we want to keep right shifting it until we hit 0, because that means we've right shifted away all the important bits. So that means we've counted the number of important bits. Okay, so let's try and build up our knowledge. So our main goal is we have this 0, 0, 0, I guess I'll just draw it like this. We have, this is our number, this is 5. And then first, we're going to use this not operator. And this not operator gives us this value, 1, 1, 1, 1, 1, 0, 1, 0. Okay, but this value is not enough. We want to AND it. So here is our AND. We want to AND it with this number so that we get our final result. Of 1 or 0, 1, 0, and all of these are zeros. Okay, and then to do this, we started to talk about how are we going to create this mask. So we realized that this is the same thing as 0, 0, 0, 0, 1, 0, 0, 0, minus 1. So then our question became, how do we figure out this value right here? And then we're going to do that by having a left shift. So we're going to have 1, and we're going to left shift it by the number of important bits. So these are the important bits that we care about. So then the question became, how do we figure out the number of important bits? And how we do that is with a number, with our original number. So here is our 5. So with our original number here, we're going to keep right shifting it. So let's pretend that this is the end of the number. And then what we do is we're going to keep right shifting it until we hit 0. So here's right shift by 1, right shift by 2, right shift by 3. And then you can see here, when we right shifted by 3, all of these are now garbage, and we see 0. And that's how we get 3. Okay, let's try coding this out. So it seems like the first step is to figure out the number of important bits. So we'll write this out. Let's say number of important bits is 0. So we'll make a copy first. So int temp, we'll make it the same as num. And then while this temporary is not equal to 0, so remember our goal is to stop when it equals 0, we're going to right shift it by 1. So this is the same thing as temp is equal to temp, right shift by 1. Okay, so after we've done that, we can now call num important bits. We found 1 important bit. And this stops, again, when our temporary becomes all zeros. That's after we've shifted all our number of important bits away. Okay, so now we have a number of important bits, and we want to create our mask. So our mask is going to be equal to this number minus 1. So some number minus 1. So this number is going to be equal to 1 left shift by the number of important bits. So remember, left shift here will push your 1 to the left by 1 every single time if we left shift it by 1. So now we left shift it by 3, so the number of important bits that we found to get to here. And then we minus 1 here to get our mask of all 1s here. Okay, so now that we have our mask, we can finally do our binary not, so our inverter. So this inverts our binary number, and then we want to throw away everything that's not important. So we do that with an AND of our mask. So we AND our mask. And this is the final number that we're going to return. Okay, let's give this a go. So that's kind of a crash course on some bitwise operators that we have. And then if you're wondering, what the runtime of something like this would be like, we can kind of give a high approximation that of the fact that integers store 32 bits. So that means no matter what, this while loop here will finish within 32 iterations. Because let's say it's 32 bits and you have a number like this, you'll just keep right shifting it by 1. So you right shift it by 1 and then you right shift it by 1. So it'll go all the way to the end, and this will never be more than 32 bits because integers only store 32 bits. So technically, you can say that this has a runtime of constant time because we know exactly it's not scaled by whatever number you have. It's always a constant. Okay, I think that's it. And let me know if you have more questions, and I'll see you on the next one.